All right, so we've talked about string theory before, but today we're leveling up. We're talking about superstrings. So what's with the super? Well, it turns out the original theory was kind of incomplete. It was missing something absolutely crucial for building a universe that looks anything like ours. Let's dive in.
I mean, imagine this. What if your best, most elegant theory of everything was missing half of everything? That's exactly the spot physicists found themselves in. The first versions of string theory were beautiful, sure, but they had this gigantic hole. They could describe forces, like gravity and electromagnetism, but they had absolutely nothing to say about, well, us, or this desk, or literally anything made of matter.
Yeah, this first attempt is what we call bosonic string theory. And don't get me wrong, it was a massive breakthrough mathematically, but it was just an incomplete picture. Think about it like this. It gave us a theory for all the messengers, but it forgot to include anyone to deliver the messages to. It was this whole framework of forces just floating in a void with nothing to act on.
So here's the absolute heart of the problem. You've got two kinds of particles in the universe. You've got bosons, which are the force carriers, photons carrying light, for example, and then you have fermions. That's everything else. Electrons, quarks, the stuff we're made of. And the original bosonic string theory, it could only make bosons. It had literally 0 fermions. So if you want to build a universe with people in it, you've got to figure out how to get these strings to vibrate in a whole new way, a way that can produce matter.
So how did they pull it off? Well, this equation right here shows the key. Now don't worry about understanding all the math. Just look at that new symbol they added in, the psi term. That little thing represents a brand new ingredient, a fermionic field. The best way to think about it is like they taught the string a new song. They give it a new kind of vibration, a new musical note it could play. And that new note is what allows a vibrating string to become a particle of matter.
Okay, but you can't just throw a new ingredient into the mix without changing the recipe, right? You need a whole new set of rules to make it all work together. And that's where this thing called superconformal algebra comes in. Just think of it as the upgraded operating system for the string. The super part, that comes from an incredibly deep idea called supersymmetry, which is this profound link between matter particles and force particles. And this algebra, well, it's the mathematical engine that actually makes that connection happen.
But here's where things get really, really interesting. This upgrade wasn't so simple. Adding fermion to the string actually created a huge complication, a choice. It forced physicists to decide how these new fermionic fields would behave, and that choice basically splits the whole theory into two completely separate worlds, or what they call sectors.
So to get a handle on this, picture a little fermion just cruising along a closed loop of string. It does one full lap, right? And it gets back to where it started. Now, here's the question. When it gets back, is it exactly the same as when it left? Or has something about it flipped? Has it come back kind of inverted? Believe it or not, the answer to that seemingly simple question literally splits the universe in two.
And this is, for my money, one of the most amazing and just weird parts of the whole theory. In one version, called the Neveu-Schwarz sector, or just NS for short, the fermion is what we call anti-periodic. It flips. And strangely enough, those kinds of vibrations end up creating the force particles, the bosons. But in the other version, the Raymond or R sector, the fermion is periodic. It comes back completely unchanged. And those vibrations, they create the matter particles, the fermions. It's wild. The internal rules for how a fermion travels on a tiny string directly determine what kind of particle we see out here in the real world.
And this right here just drives the point home perfectly. Take a look at these two equations. The only difference, the only thing separating the rulebook for a universe of forces from the rulebook for a universe of matter is that one is a plus sign and one is a minus sign. I mean, think about that. The entire nature of reality hangs on that tiny little symbol. It is just mind-blowing.
Okay, I know what you're thinking. The math is starting to get pretty hairy with all these new fields and sectors and rules. But physicists found an incredible shortcut. It's like a mathematical magic trick that, get this, only works in the two-dimensional world that exists on the surface of the string.
And, even the source material calls it a rather surprising equivalence. It's not an obvious thing. It's this really deep, fundamental feature of two-dimensional physics, and it just cracks open a whole new, powerful way of actually doing the calculations.
Yeah, the concept is called bosonization, and honestly, the best analogy is to think of it like a mathematical Rosetta Stone. It lets you take a really complicated theory written in the difficult language of fermions and translate it perfectly into a much simpler theory
written in the language of bosons, and you don't lose a single bit of information in the translation. It's an unbelievably powerful tool for just figuring out what the heck the theory is trying to tell us.
All right, so we've got our new ingredients, our new rules, and even this cool mathematical shortcut. But for this whole beautiful structure to be a real theory of physics and not just a pile of random equations, everything has to fit together perfectly. It has to be mathematically consistent. And it turns out demanding that consistency, well, it leads to a requirement that is just stunning.
You see, the math of quantum mechanics is incredibly strict. It's really unforgiving. You just can't have things like infinities or paradoxes popping up in your final answers. That means your theory is broken. And in string theory, making sure that everything behaves itself and gives you sensible answers, that forces an incredibly rigid constraint on the very fabric of the universe. A big part of this comes down to canceling out these weird mathematical artifacts called ghosts. Now, they're a necessary tool you have to use in the middle of the calculation, but they absolutely must disappear from the final physical answer. And as you can kind of see from this equation, getting everything to cancel out perfectly, making the ghosts vanish, it only works if one particular variable, that d, for the number of space-time dimensions, has a very, very specific value. And that value is 10. Not 9, not 11, 10. The theory just completely breaks down in any other number of dimensions. The math only balances, the ghosts only vanish, if the universe has exactly 10 dimensions of space-time. And this is so important. This isn't some number physicists just picked out of a hat. It's a requirement. It's a demand coming directly from the mathematics.
So, let's take stock. We've got all the pieces on the table now. We have strings that can be both matter and forces. We have the two different rulebooks, the Ramond and the Navier-Stokes sectors, and we have the 10-dimensional stage that they have to perform on. Now, finally, we can start putting it all together and build the final product, the actual consistent superstring theories.
And when you combine all these ingredients in the ways that the math allows, you don't just get one theory, you get a small family of them. You can see here there's a type 1 theory, which is cool because it uses both open-ended strings and closed loops. Then you have the type 2 theories. They only use closed loops, but they come in two flavors. There's type 2a, which is basically ambidextrous. It doesn't have a preference for left or right. And then there's type 2b, which is chiral. That means it does have a built-in handedness, a preference for left versus right, which, interestingly, is a feature our own universe seems to have.
So let's just do a quick recap of the journey we just took. We started with a theory of just forces, but it was missing all the matter. So we added matter, the fermions. But doing that required a brand new, more powerful kind of symmetry. And that symmetry forced us to make a choice, splitting the theory into two sectors, one for forces and one for matter. And then, to make sure the whole thing didn't just collapse into a pile of mathematical nonsense, the universe itself had to have 10 dimensions. It was only after all of that that we could finally construct this handful of consistent superstring theories.
And of course, all of this leaves us staring at the biggest, most obvious question of them all. We experience 3 dimensions of space and 1 of time. That's 4. So if superstring theory is right, where in the world are the other 6 dimensions? Well, that is a story for another time. Thanks for joining me.